presentation is about the metal carbonyl bonding and the IR frequency. What are the learning objectives or what is the motive behind studying about this metal carbonyl complexes is what are the different type of synthetic methodologies which are involved in the formation of metal carbon bond and metal carbonyl complex. Next is there are different types of synthetic methods which help in the formation of carbonyl complexes and what is the effect of all those synthetic methods on the bonding characteristics of those carbonyl compounds. Then reaction conditions which are required, and the fourth is what is the different types of organometallic compounds and the different types of bonds or the possibilities whether we talk of sigma bond or we talk of pi bond in case of metal carbonyl complexes. Now, what are actually metal carbonyls that we should know? Metal carbonyls are the coordination complexes of the transition metals in which the carbon monoxide is the major ligand. The metal carbonyls are useful in organic synthesis because they are majorly used for two major type of homogeneous catalysis reactions, which is their main application. One is the hydroformylation reaction and second is the Reppe chemistry or Reppe type of reaction. In these two reactions, carbonyl plays a very important role. In the second point in this slide, the thing that has been explained to you is the type of bonding mode that the carbonyl can have. Now, majorly carbonyl can have one terminal mode. In this terminal mode, there is a existence of triple bond between carbon and oxygen and the carbon is attached with the metal. So, there is a single bond between metal and carbon. Now, in second type, that is a bridging mode. Bridging mode can be of two types. One is the mu2 type of bridging mode in which the carbon and oxygen are having double bond and the carbon is attached with two metal atoms. Third type of bridging mode is mu3 bridging mode in which, as you can see, between carbon and oxygen you have a single bond and the carbon of the carbonyl ligand is attached with three metals. So these are the three different types of bonding modes that can exist in carbonyl compounds. Next is what is the role of IR spectroscopy in this carbonyl compound? First of all, we need to understand that how is bonding taking place in case of metal carbonyl. Now, when we talk of metal carbonyl, there are two major types of bond. One is the sigma bond, which is the general bond that happens between a metal and a ligand. That is, ligand donates its sigma electrons to the metal d orbitals. But the second type, which is also known as the synergistic type of bonding, that is also equally important. What happens in this is the metals which have the filled d orbitals or d electrons, that is the transition metals, they causes the back donation of the electrons to the pi star antibonding vacant orbital of the carbonyl. Now, in some of the upcoming slides, we will see or we'll study about the molecular orbital diagram of carbonyl ligand, in which we will see that in that carbonyl ligand, we have the presence of that pi star vacant antibonding orbital. And because of that particular orbital only, this type of synergistic pi banding is possible, which actually is responsible that carbonyl can show multiple type of bonding, that is it can show triple terminal type of bridging mode as well as it can show bridging mode, that is mu2 and mu3 type of bridging. On your right hand side you can see the IR spectroscopy of two carbonyl compounds have been given. What is the thing that you need to focus on that is in the first example, in the manganese one, you can see all the carbonyls which are present on each of the manganese ligands are terminal. So, this terminal carbonyl bridging mode has a specific frequency value, that is, it comes between 1900 to 2100 centimeter inverse. See, and because there are 10 carbonyl atoms which are attached with two manganese, this is a broad spectrum. What is the point to be noted here is that terminal carbonyls have a specific frequency. So from the IR frequency value, you can understand whether the carbonyl in your given compound is in terminal mode or it is in bridging mode. Why? See the second figure. In your second figure, you can see that terminal bridging mode comes between 1900 to 2100 centimeter inverse. But whenever the carbonyl is present in the bridging mode, its frequency will be very, very less. And you can see it will come in between 1600 to 1700 centimeter inverse. So just by knowing the IR spectroscopic value in a particular given organometallic compound, you can easily identify whether the carbonyl is in terminal mode or whether it is present in bridging mode, or both types of modes are present in your complex. This will give you a better idea. See, this is the terminal mode. What is the frequency value between carbon and oxygen mode is given? It is between 1850 to 2120 centimeter inverse. This is a mu2 type of bridging. What is the frequency value given? It is between 1700 to 1850 centimeter inverse. Next, mu3. Mu3 means your carbon in the carbonyl is attached with 3 metal centers. So its frequency value is 1620 to 1730 centimeter inverse. So in the lower these examples, you can see just by knowing the frequency value, you can identify the type of bridging modes in your carbonyl complex. In this, they have said that there are two major factors on which this carbonyl binding depends. First, and the most important thing that we need to consider is the charge on the metal. That is, the amount of negative charge or the electron density present on metal plays a very important role in determining the frequency value also. First is one frequency value tells you about terminal and bridging, but within that frequency value also you can have the variation depending on the electron density present on metal. And second factor is the effect of other ligand. But out of the two factors, most important is charge on metal. Why? Because see, whenever the electron density on the metal will increase, so what will happen if electron density is more? Metal will have more tendency to donate its electron for the pi back bonding, that is the second type of bonding, to the pi star antibonding carbonyl orbital that is present vacant. So if this back donation happens, what will happen? This will increase the metal carbon bond strength, but this will decrease the carbon oxygen bond strength. Always remember, when you have more electron density, that means metal will have higher tendency to donate its electrons, and if metal will have higher tendency to donate its electrons, that means between metal and carbon there could be formation of an extra bond. So whenever there is extra bond formation, that will increase the strength of the bonding. But what is happening to the bond between carbon and oxygen? The strength of that bond is decreasing because in terminal position it was triple bond. But when in bridging there is more of back donation, this carbon oxygen bond strength decreases. So if bond strength decreases, your frequency will become lower. So in short, you need to know whenever more electron density, that means more amount of back bonding is there possible in a given carbonyl compound. That means its carbon oxygen bond frequency will be very low. See in the first column, as we are moving from nickel to cobalt to iron to manganese to chromium, as the charge on the metal, negative charge on the metal is increasing, the electron density on the central metal is increasing. That means there will be more of back donation. More of back donation means the carbon oxygen bond strength will decrease, metal carbon bond strength will increase. That means ultimately your frequency of carbon oxygen bond is decreasing. Correct? In second one also, second column, always the free carbonyl will have maximum stretching frequency. Why? Because carbonyl is free, carbon and oxygen in the carbon monoxide are in triple bond, so it will have highest frequency and highest bond strength because it is not attached with any metal. There is no pressure on this bond. But as soon as you can see this free carbonyl gets attached with the metal, this is a positively charged metal. Positive charge means electron density is less on the metal. Then you have a neutral complex. Now in neutral complex, the electron density on metal will be slightly higher than in positively charged metal. Next, two vanadium and titanium complexes are having negative charges. Now negative charge means electron density on the metal is increasing. So as we are moving from positive to neutral to these two negative charge species, the electron density on your metal is increasing, more amount of back donation is there, and as we know, if there is more amount of back donation or more back bonding is possible, so the frequency between carbon and oxygen will decrease. So this is the major factor how your charge on metal affects the value of your carbon oxygen stretching frequency. So this is the molecular orbital diagram which I was talking about. As you can see, this is a carbon monoxide ligand molecular orbital diagram. What is happening in this? It consists of highest occupied molecular orbital. I think you all are aware of this. That is, what is the orbital which is the which is of high energy and which is maximum filled, it is your 3 sigma orbital. And what is the lowest unoccupied molecular orbital? So your pi star is lowest in energy, which is not occupied by any electrons. So that means whenever a metal will be forming a carbonyl bond with carbon monoxide ligand, there are two types of bonding that will take place. One, the ligands or the electrons which are present in the highest occupied molecular orbital of carbonyl molecule will be donated as the sigma bond to the metal. It will be forming the sigma bond, but at the same time the metal which is in lower oxidation state, suppose 0 and +1, whose electron density is high, will be able to donate its electrons to the lowest unoccupied molecular orbital, that is your pi star orbital of carbon monoxide ligand, which is responsible for the formation of pi star antibonding orbital. So in case we have two types of bonding. So in this particular video, it will be explained to you that how to do the electron counting of high nuclearity carbonyl complexes. What is HNCC known for? It is known for high nuclearity carbonyl clusters, and LNCC is known for low nuclearity carbonyl clusters. Now, when we talk of high nuclearity carbonyl clusters, what all things are there is high nuclearity means we are considering a particular metal complex which have higher number of metal centers. That is, more than 2 metal centers are present in your carbonyl complexes. Correct? So, we will see this video. In this particular video, he is just explaining first that what is the difference between low nuclearity carbonyl complex and high nuclearity carbonyl clusters. So, high nuclearity carbonyl clusters says the number of metal centers which are present are much more than 5. That is, it is more than 4 or more than 5 number of metal centers are present. Some of the examples of these carbonyl clusters are as follows. That is, the first one will be, let him start first, just wait for a few seconds maybe. I think we will be taking some ruthenium or rhodium complexes because these are the metal complexes which actually can exist in high nuclearity carbonyl cluster complex, right? Which have the capacity that it can bind to large number of carbonyl ligands. So first example is, as I said, rhodium 6 CO 16. So this is high nuclearity because number of metal atoms is 6. So, what is the step 1 for doing the electron counting in these type of complexes is, first of all, we need to find out the total number of electron counting in this particular complex. So, what is the total number of electron count? See, TEC stands for the total electron count in this complex. So, what is the total electron count in this complex? See this. We first need to consider the number of valence electrons of the metal atom. So the number of valence electrons in rhodium is so in this he is also explaining that this is a simple carbonyl clusters, but high nuclearity carbonyl clusters means there could be the presence of some of the interstitial ligands. What do you mean by interstitial ligands? Hydrogen, nitrogen, carbon, which are smaller in size. There is always a possibility that sometimes in high nuclearity carbonyl clusters, these types of small ligands are also present. But in this one, it is not present. So this is a simple carbonyl clusters in which no interstitial ligand is present. So in step 2, poly-electron count will be there. PEC, known as polyhedral electron count. And how this is done? So PEC, the formula is, first of all, you need to calculate the total electron count of your carbonyl clusters. Then you have to subtract n into 12. Now what is n here? N is the number of metal atoms in these clusters which is present. So suppose for this particular complex, N is your 6 because 6 rhodium or 6 metal atoms are present. See, N stands for the number of metal atoms which are present. Okay. Next, so PEC divided by 2. So once you get the total electron count, and from this formula you can calculate the polyhedral electron count. Then by dividing the polyhedral electron count number by 2, we can get or we can reduce it to a figure which can give an idea of the type of structure that this particular complex will be having. Suppose for this particular complex, if your PEC by 2 comes out to be N minus 1, that is N is the number of metal atoms, so it is 6. If your PEC by 2 comes out to be 5, we can reduce it as 6 minus 1, that is N minus 1, 5. So that will represent that it is a supercloso type of a structure. Suppose if it comes out to be N, PEC by 2 just comes out to be 6. So it will be N, it will be a hypercloso structure. So in this way, we can have closure structure also, N plus 1, if that comes out to be N plus 1 closure structure. If that comes out to be N plus 2, it will be a nido structure. N plus 3, arachno. Now these things you need to know. N plus 4 will be hypoclosure structure. N plus 5 will be a clado type of a structure. Clear? So this is how we can identify what is the main structure of the high nuclearity carbonyl cluster just by knowing the PEC by 2 value which is coming out to be there. So for this particular complex RH6 CO12, the total electron count is coming out to be first see this. He's just explaining the outline of this. So it is 6 into 9 because 6 rhodium atoms are there, and in the valence shell electron count of rhodium is 9 plus 16 into 2. So what is coming out? The total electron count is coming out to be 86. Now from here, when we need to calculate the polyhedral electron count, that will be total electron count minus n into 12. So that will be 86 minus n is 6, that is 6 metal atoms are there. So 6 into 12. Okay. So 72. What is the number? 14. Now we have to do PEC by 2. So when we divide this 14 by the number of 2, what is the number coming out to be? It is 7. So can we deduce 7 in terms of 6? That is, we can easily write 7 in terms of 6 as it is 6 plus 1. So 6 plus 1 is what type of a structure? We can also determine that from it. 6 plus 1 will be a closo type of a structure. So we can say that particular complex is having a closo type of a structure. In this further, a second example has also been come, and this is very important from entrance perspective also, from CSIR perspective also. In this, we see he's calculating the second one, that is OS3CO12 type of a complex. He will be calculating what type of a structure in this, following the same rule that we have done for the last example.